In this video, I am going to discuss a little bit about the basic of linear algebra. So when we say about linear algebra, it will tackle all about vector and matrices. So what is a vector? So actually a vector is only a scalar plus direction. What do you mean by that? Scalar is it's only a magnitude, like a magnitude. Example, speed versus velocity. As you might remember in your physics, speed is just a scalar value. For example, the car runs at 70 miles per hour. That's the speed. Whereas for velocity, you can say that the car is running at 70 miles per hour going east or west. So here it shows a direction where it is heading. Okay, suppose we have a point, for example, in a plane 1 2 3 4 5 1 2 3 4 5. Your point is 2 5. So actually, 1 2 1 2 3 4 5, so it's here. In vector representation, it usually do like this with a bracket 2 5, and when you represent it in a plane, it has this direction from the origin. So that now this is the vector 2 5. So as you can see, it has already the direction. All right, a vector is also a matrix. It's also a matrix. It's considered matrix with a column 1. For example, this value 10 5 is 2 by 1. So this is the row and this is the column. All right, now let's go to linear algebra basic operation. We'll talk about addition and subtraction. In adding two matrices, you should remember that the two matrices should be the same size. For example, 10 5 plus 1 2. When adding these two, just it's like an element wise. This one is for row 1 column 1, and the second matrix is also row 1 column 1. So just like that, when you add this one, it should have the same size. So 11 and 7. Let's do another example with two column 10 2 5 3 4 1 plus 1 1 1 2 2 2. As you can see, it should be in the same size. So element wise, just add same location. Okay, what's the answer? 10 plus 1 11, 1 plus 2 3, 5 plus 1 6, 3 plus 3 5, 5 and 3. You can add two matrices with different size. For example, 10 to 1 plus 2 3 4 5. This one is impossible to do unless you want to add 0 here or here, but based on rule, it should be the same size. For subtraction, it's the same, just also subtract it. Okay, now let's go to multiplication. Matrix product, they call it, I think, matrix product, is a bit different. In multiplication, the first matrix, the number of column, this is 3, and is equals to 3, should be equals to the number of rows in the second matrix. This is M3. As you can see, this is column 1, column 2, column 3, row 1, row 2, row 3. The size of this is 3 by 3, and the size for the second matrix is 3 by 2, and the output of the multiplication will get the outside one. Okay, so the output will probably be 3 by 2 size. So let's do that. In matrix multiplication, we will do something like this. The first column and first row go here, go here, go here. Okay? Okay, let's do this. 1 times 1 plus 2 times 1 plus 3 by 1. It is equals to 6. Now let's do the other one. 1 by 2, 2 by 2, 3 by 2. Okay, 1 by 2 plus 2 by 2 plus 3 by 2. And this is 12. Okay, let's go to the next one. Here, here, here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is 15. Okay, again, this one. Sorry, it's a bit messy already. Okay, 4 times 2 plus 5 times 2 plus 6 times 2. How much? So total is 10. Okay, last one. Do this together. 7 times 1, 8 times 1, and 9 times 1. 7 times 1 plus 8 times 1 plus 9 times 1. Okay, this is 24. Okay, and the last one to the next column. 2. 7 times 2 plus 8 times 2 plus 9 times 2. So this is 48. So our output now, the size is 3 by 2. As you can see, this is, the row is 3 and this is 2. For division, it's similar to multiplication. It's just that instead of multiplying the two, you will use division. Okay? Alright. Let's go to multiplication of scalar to a matrix. Scalar times matrix. For example, some value like 5, and you have a matrix 1, 2, 3, 4. So what it will do is just multiply each value. Okay? This one, it's like scaling, making it bigger, scaling to 5. So the output would be something like this: 5 times 1, 5 times 3, 5 times 2, and 5 times 4. Output would be 5, 15, 10, and 20. So this value scale up by 5. So that's all. This topic is all about determinant. Why we discuss about this? Because this determinant can be used later in our discussion about inverse matrix. So determinant can be applied only for square matrix. We have a lot of term here, but don't worry, you will get used to it. Square matrix meaning the number of row is equals to the number of column. For example, this 1, 2, 3, 4, 5, 6, and 8, 9. Okay, the number of row is 3 and the number of column is 3, or 2 by 2, or 5 by 5, or 10 by 10. That's what we called square matrix. Let's start with 2 by 2 matrix. For instance, we have this matrix. How to find the determinant is just multiply crossover. Okay, 1 by 5 minus 2 by 4. The output of the determinant is always a scalar value. Okay, it will not output as matrix size. 6, 4 times 2, 8. Okay, the answer is -2. How about this? 5, 10, 1, 6. Can you answer? Okay, let's do this here and here. 5 times 6. Remember the sign. Always remember this negative sign. 10 times 1. 30 minus 10. 6 times 30. So the answer is 20. How about for 3 by 3? It's a bit complicated. It's a long process. Suppose we have this 3 by 3. I'll make it small value so I won't have a trouble multiplying later. 5 to 1. Okay, this is the 3 by 3. The first thing you need to do, let's have a different color. First thing you need to do is use this top row. Okay, first get the top row, first column, then do the 2 by 2 matrix. Okay, 1 times, okay, I changed this to bracket, times, do that 2 by 2 determinant process. 4 by 1 minus 2 by 2 minus, okay, next we are going to do is the second column, then do this 1, okay, 2, do the 2 by 2 matrix, 2 minus 4 times 5 plus, okay, make sure you watch out this, the first is minus, the next one is plus. Okay, let's have a different color. Now for the next column, the last column, which one does not involve, oh sorry guys, sorry, I have a mistake, I just realized. Okay, let's delete this first. Okay, go back, I'm sorry. Okay, I delete this. Okay, go back to column 2. Make sure that, oh sorry, for this column 2, as you can see, this is the value column 2. We should exclude this column 2, so exclude. So we will do these things. Okay, 2. Okay, now it is 2 times 1 minus 2 times 5. Okay, that's it. Plus, okay, so this is the one, the last row. Let's use different color. The last row, last column, I mean, this is the time we will use this. Okay, 1, cross this, 2 by 2 minus 4 by 5. Okay, let's do this. Okay, this is 0, negative 16, and negative 16. The answer would be 0 minus negative 16 plus negative 16. How's that? Goes to 0. Recap for 3 by 3 column. For example, you have this A, B, C, 3 by 3 matrix, sorry, E, F, G, H, I. For 3 by 3, you always need to do the first one. Select the top row. Okay, select the top row. Then, once you selected that, make sure, for example, you select the top row, make sure to cross out all the values belongs to this row and all the values belong to this row. Then put back the EF, HI. Then do the 2 by 2 operation. Okay, you know already the 2 by 2 operation. Next is do the second column. Okay, second column, this is B. I mentioned delete the one that belongs to this row and belong to this column. Okay, D, G, F, I. Proceed for 2 by 2. you know the process, you know the next step. So it is minus, then plus. Okay, next process for C. Delete for the first row and delete for the last column. TE, sorry, let's change the color. Then do for 2 by 2. Okay, how about for 4 by 4? You can try for 4 by 4. It's a long process, but we can try it here. Okay, let's do this 4 by 4. Let's do it together. Okay, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Okay, what we need to do, as I said, get this first column. Okay, consider A, then cancel all the column, F, G, H, J, K, L, N, O, P. Then after that, okay, it's a long process. I think you can try. I may stop in this procedure. A times. Then this one is 3 by 3 matrix. Then do for 3 by 3 matrix. It's really a long process, guys. So F. So it would be F times K L O P minus G. You know the process, you know the pattern. L, what's this one? M, P. And this, where are we? G, L, and P. M, P plus H. H for J, K, and O. Okay, that's our first process. Now let's do plus. Okay, let's do the second column. Okay, column. Where are we? Okay, I might copy this again. Okay, this is B, C, D. Sorry. I said I need to remove that. Okay, sorry. I need to remove that, but I need to retain E, I, M and remove that column. G, H, K, L, O, P. Okay, well, let's do then P. Do this square matrix, a 3 by 3 matrix. Yeah, do E first. E, okay, this one. K time K, L, you will do later. Okay, minus, where are we? It's G, I, L, M, P, where then H, I, K, and M, O. Okay, then minus, and so on and so forth. I know you will do. I know you can do it, but I will stop it here since it's already a long process. That we know all about determinant, we can proceed to inverse of our matrix. Okay, the rule here is, for example, for 2 by 2 matrix A, B, C, D, the inverse of this is 1 over, let's call this as A, the determinant of A times, swap these two, D, A, then put the sign for negative B and negative C. Then proceed for scalar multiplication. Okay, for example, we have this 1, 2, 3, 4. Let's find the determinant for this. Determinant for 1, 2, 3, 4. Remember, if you can still remember, 1 times 4 minus 2 times 3, 4. 3 times 2, 6. So it is negative 2? Negative 2, I guess. Okay, now we got that. 1 over negative 2. I said swap this 2 for 1 put negative sign on -2 and 3. Okay, let's do this scalar multiplication. Okay, let's multiply. So actually it is, so we'll not get confused, -1/2 4 -2 3 1. Okay, let's do it together. -1/2 times 4, -1/2 times -2, -1/2 times 3, and -1/2 times 1. What's that? You can solve. Let's solve together. -2, this, how about this? It's 1. How about this? It's -3/2. How about this? It's -1/2. Okay, this is our answer. Oh, I spot a wrong answer. Sorry, I mentioned right. It should be negative, and this should be negative. This should be negative, and this is positive. So this is the answer. When a matrix is multiplied by its inverse, A times inverse, it is always equal to identity matrix. Same goes with, for example, we have for a normal number like 4. What is the inverse of 4? It's 1/2, 1/4. Okay, 4 times 1/4 is equals to 1. Same goes with matrix. However, this identity matrix is diagonal. For example, 1 0 0 1 1 0 0 0. This is what we call identity matrix. If you multiply the matrix of its own inverse, it will result to this. Okay, let's prove that. Let's prove. Okay, 1 2 3 4. Okay, our A is 1 2 3 4. Inverse of A is -2 1 3/2 and -1/2. Let's do this. 1 2 3 4, -2 3/2 1 -1/2. Remember your product, matrix product operation. Let's do that. Okay, let's do this here and here. 1 times -2 plus 2 times 3/2. This one and this one. 1 times 1 plus 2 times -1/2. Okay, 3 times -2 plus 4 times 3/2. Last one. 3 times 1 plus 4 times -1/2. Let's do this. This is -2. This is 3. 3 minus 2 is 1. Okay, how about this? This is 1. This is -1. 1 minus 1, 0. How about this? -6. This is 4 times 3, 12, divided by 2, 6. What's this? It's 0. How about this? 3. 4 divided by 2 is -2. 3 minus 2 is 1. And we got this identity matrix. Okay, guys. The last topic is all about transpose. Transpose of a matrix. What do we say transpose? It's similar to the function in Excel. For example, you have the values from this column and you want to transpose it in this column. So same with matrix. For example, you have this matrix 1 2 3 4 5 6. What's the size of this? 3 by 2. Correct, 3 by 2. When you transpose this, just rotate. I just imagine it to rotate. Okay, now it becomes 1 2 3 4 5 6. So you can see the 1 3 5 becomes the row, and 2 4 6 becomes the row. Alright, when you have this 3 by 2, the transpose, the size would be 2 by 3. Okay, I give you last example. What if you have this 1 2 3 4? What's the transpose for that? What's the size of this? Correct, 3 by 1. The transpose should be 1 by 3. So it's just 1, 2, 3, 4. Right. How about for 2, 3, 4, 7, 8, 9, 10, 11, 12? How about for this? What's the transpose for this? Okay, just do the same. 2, 7, 10, 3, 8, 11, 4, 9, 12. Since it's a square matrix, 3 by 3, the output was also 3 by 3. Okay. Before I forgot, the symbol for transpose is this T. For example, you have this A. The transpose of that is A raised to T. Some uses this apostrophe. So you might confuse if you found this, meaning this is transpose. Alright. The first property of transpose, of matrix transpose, is number 1, A times T, transpose of this, and the transpose is always equals to 1. It's always equals to A. It's okay. For example, I have a transpose as I have a value of, I make it simple now so it would be easier. I have A. The transpose of A is 1, 2, 3. Now this is my AT. Okay, my AT is 1, 2, 3. 1, 2, 3. The transpose of that, of course, go back to original. Transpose this to original. 1, 2, 3. And this is the answer. So that's why this transpose is always equals to. The next property is K, some constant, some value, AT is equals to KAT. Okay? For example, I have this 5. I multiply it, sorry, I might. Okay? 1, 2, 3, 4, 5, 6. Okay? The transpose of this one, I might multiply first. 5, 10, 15, 20, 25, 30. And this is your key A. And you are going to transpose that. What's your transpose? It's 5, 10, 15, 20, 25, 30. And this is my answer. Let's prove that it's equal to this one. Okay, K, let's put 5 outside. What's the inverse of AT? It's 1, 2, 3, 4, 5, 6. Okay, am I right? This is the inverse. Okay, yeah. Then multiply. Now it's 5. 5 times 3, 15, 25, 10, 20, 30. And we are done. So you can see these are equal. So we prove that this is really correct. The next property is this. Matrix A plus or minus B transpose is equals to individual transpose B T. Okay, let's prove it. Suppose we have A. Okay, A 1, 1, 2, 2, 3, 3. And B is 2, 3, 3, 2, 1, 1. Okay, A plus B. Let's do this equation first. A plus B. Remember in your that we have discussed the addition, matrix addition, just element wise. A plus B. What is A plus B? 1 plus 2. Just element. Okay. 1 plus 2 is 3. 1 plus 3 is 4. 2 plus 3 is 5. 2 plus 2 is 4. 3 plus 1 is 4. 3 plus 1 is 4. Okay? 1, 2. Maybe I made a mistake, but it's alright. And what's the transpose? Let's do the transpose for this. And the transpose for this is... No, sorry. I'll put it below. The transpose for that is 3, 5, 4, 4, 4, 4. Oh, this one and this one. Okay, right. Let's do this second equation. Let's prove. What is the transpose of AT? What is the transpose of A? Sorry, I always have a mistake. 1, 2, 3. 1, 2, 3. Plus, what is transpose of B? What's the transpose of B? 2, 3, 1. 3, 2, 1. Then let's do the addition operation. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 1 is 4. 1 plus 3 is 4. 2 plus 2 is 4 and 3 plus 1 is 4. Let's see if they are the same. Okay, alright, we got it. They are the same. And we proved that these two are equal. The next property is A times B is, reverse this one, B times T and A times transpose individual. Okay, make sure that you change the position. Right, let's prove it again. Suppose we have A is 1, 2, 3, 4, 5, 6. B is 6, 5, 4, 3, 2, 1. Okay, I might change this. I might change some value. 1, 1. Okay. Alright. I have this 2 by 3 and 3 by 2. This is a sample. I'm not using a square matrix for now. So I just want to prove that it also applies for non-square. Okay, let's do this. A times B. As you might remember, for matrix multiplication, I said that the number of column should be the number of row. Okay? Alright. Let's do this, guys. We're almost done. Don't worry. 1 times 6 plus 2 times 3 plus 3 times 1. Okay. And we sum this 15. Then let's go for the next one. 1 times 5 plus 2 times 2 plus 3 times 1. And this is 12. Let's move here. Okay. Now let's do for the second column. We're done with the first column. I will remind you that this is 2 by 3, so the output would be 2 by 2. Get outside. Alright. Oh, have a patience. Let's do this together. 5 plus 2 times 2 plus 3 by 1 and 4 times 5. I should have used a smaller number, guys. Sorry for that. But and this is 5 plus 4, 9 plus 3, 12. Okay. This is 20 plus 10, 30, 36. Okay, we got this. AB. Then the transpose for this. The transpose for it, sorry, is 15, 12, 12, 36. Let's prove that these are the same with this one. Let's do the transpose for BT. Sorry, I always have this mistake. Why? Sorry, I'm still practicing English. Okay, BT, transpose of BT, 6, 3, 1, 5, 2, 1. And transpose of AT, transpose of A, it's 1, 1, 4, 2, 3, 5, 6. Let's multiply both. Okay, I make sure that we have a boundary here. It's different. Okay, now let's do this. BT times AT, do the matrix multiplication. 6, 3, 1, 5, 2, 1 times 1, 4, 2, 5, 3, 6. Okay. Yeah. 6, 3, 1. Okay. 6 times 1, 3 times 2, plus 1 times 3. How about this? 5 times 1 plus 2 times 2 plus 1 times 3. For the next column, let's use another color. Okay, 3. Okay, 6 times 4 plus 3 times 5 plus 1 times 6, and 5 times 4 plus 2 times 5 plus 1 times 6. So let's do this together. 6 plus 6, 12, 13, 14, 15. 24 plus 15 plus 6, 45. Next is 5 plus 4 plus 3, 12. I'm excited. What's our output? 5 times 4, this is 20. 20 plus 10 plus 6, it's 36. Are they the same? Oh my gosh, it's not the same, guys. Sorry. Where did I go wrong? Okay, where did I go? Oh, found ready. How come I do this? This is wrong. Sorry. I made a mistake again. Let's do this again. Okay, this should be this one. 4 times 6 plus 5 times 3, 6 times 1. It's okay to make a mistake, right? What is this? 6 times 4, 24, 15, 6. Okay, 24 plus 15 plus 6 is 45. Yeah, we found it. I think we're almost there. This is 45, and when it will be transposed, the 45 will be here. Okay, let's see if they are the same. 15, 45, 12, 36. 15, 45, 12, 36. We made it. Yay, thank you. In this video, I will explain some of the properties of a matrix. So let's start with addition. For example, you have A plus B is equals to B plus A. So they can be interchanged. But for multiplication, they're not the same. Remember that AB is not equals to BA. They are not the same. They're totally different, because in multiplication, position matters. Okay? When you add A to its inverse, what's the answer? It's always equals to 0. Okay, remember that. And I think I already discussed this. Multiply of A to its own inverse is also equals to identity. Multiply A to its A transpose. Sorry. A transpose is go back to A. Let's move on to associative property of matrix. A plus B plus C is equals to A plus B plus C. For multiplication, A plus BC, BC is equals to ABC. Now let's move on to distributive property. For example, A, B plus C is equals to AB plus AC. Okay, this is similar to the normal algebra. Or BCA is equals to BA plus CA. Remember, order matters. You cannot interchange this. And that's all for now, folks. You can try to prove that this theorem or properties are equal. So you can try it for yourself to prove that these are correct.